Hey everybody, welcome back to the last video of electricity. So we're talking about net electric fields, and here are a little bit of notes to guide us with this topic. So when multiple source charges are near each other, the net electric field will be a combination of both charges. We kind of learned about this when we talked about drawing electric fields, but here's an example. Charge 1 exerts an electric field at the origin directed upwards because it's negative. Q2 exerts an electric field at the origin that's directed to the left because that is positive. The net electric field will be a combination of both of them. So with both of them, it'll be going some kind of diagonal way like that. Okay, so you kind of like add them together as you're doing it. Anyway, as we do some examples, it should make a little bit more sense if you are confused. So conceptual example number 18. Look at the diagram below. All the charges are positive and have the same magnitude. At the origin, which way will the net electric field be pointing? Okay. So let's first just look at 1. When we look at 1, it's positive, so it's going to be pushing it to the right. Now let's look at 2. It's also positive, so it's going to be pushing it to the right, but it's really close, so it's going to be pushing it more to the right than charge 1. Charge number 3 is positive, so it's going to be pushing it to the left. However, the net electric field will be something like this. Okay, so it'll be part B. Okay, because at the origin, more of the electric field will be going to the right than what's going to the left. All right, moving on. Look at the diagram below. Source charges 1 and 2 are negative. Which source charge? While source charge 3 is positive and all have the same magnitude of charge. At the origin, which way will the net electric field be pointing? So again, let's look at the origin. 1, since this is negative, will be pulling it a little bit to the left because it's kind of far away. 2 is negative, and it's going to be pulling it a lot more to the left because it's closer. Q3 is a positive charge. Source charge Q3 is positive. Well, actually, it's negative, so it's also going to be pushing it to the left. Oh, sorry. Q3 is going to be pushing it to the right a little bit because it's negative. Okay, so it's going to be going to the left. All right, it's going to start getting a little harder. 2 identical charges, A and B, have a positive charge. Which arrow best represents the direction of the resultant electric field at point P? Alright, so let's just look at A right now. The electric field at A, remember, everything is going outwards. So at point P, if we're just looking at A, it's going to be pushing it this way. B is also a positive, so it's doing an electric field outwards. It'll be going this way. If we were to combine both A and B, what we have is we're going to have this going straight up and everything in the X's canceling each other out. So it'll just look like it's going straight up. Okay, moving on. These are a little bit hard, so take some time to think about it and everything. Alright, 2 charges, Q1 and Q2, have equal magnitudes Q and are placed as shown in the figure at the right. The net electric field at point P is vertically upward. We can conclude that Q1 is positive and Q2 is negative. Q1 is negative and Q2 is positive. Q1 and Q2 have the same sign. Okay, so let's start with A. Q1 is positive. And again, pause if you want to try to figure it out on your own. Q2 is negative. If that's positive, that means it'd be going outward, so it'd be going like this. And Q2 would be negative, so it's pointing inward, so it'd be like this. And the net electric field would be going down like that. So it can't be A. I'm gonna erase that. Let's try B. Q1, oops, let me erase this. Q1 is negative and Q2 is positive. So if it's negative, that means it'll be pointing this way. And Q2 is positive, so it'll be pointing this way. And we can see that this checks out. In the X direction, they'll cancel out, and it'll just be going up like this. So it'll be part B. Okay, you could try part C if you want as well, but part B is the answer. All right, that one was pretty challenging, so if you're able to get that, good job. Last one here, going to take a little bit of time, but let's do this. As shown in the diagram above, a positive charge Q1 is equal to 0.004 coulombs. It's located at negative 3 meters. And positive charge Q2 is equal to 0.008 coulombs, and is located at positive 4 meters. Find the magnitude and direction of the electric field at the origin due to charge Q1. So this is the origin, and we want to find what the electric field is by Q1. It's positive, so it's going to be something like this. But let's find what the electric field is. I'm going to call it E1. Alright, so we know that E1 is going to be equal to KQ over R squared. So E1 is going to be equal to 9 times 10 to the 9th to charge Q1, which is 0.004, divided by how far it is, which is 3 meters, 3 squared. Alright, so let me put this in. 9 times 10 to the power of 9 times 0.004 divided by 9. And we get around 4 million Newton per coulomb to the right. Okay. 4 million. 4 million. Okay. Part B. Find the magnitude and direction of the electric field at the origin due to charge Q2. Okay, Q2 is also positive, so at the origin it's going to emit an electric field that's going to the left. I don't know how much, but that's what we're going to find out right now. So same formula, E2 is going to be equal to K, which is 9 times 10 to the 9th. The charge, which is 0.008, so it's stronger charge than Q1, but it is further away. It's 4 meters away, so 4 squared. Alright, let's figure out what that is. 9 times 10 to the power 10 to the 9 times 0.008 divided by 16, and we get around 4,500,000 to the left. Okay, great. So now find the magnitude and direction of the electric field. So E net will be equal to E1 plus E2. So E1 is equal to 4 million. And it's going in the positive direction, so that's positive. Plus E2 is going to negative, so it's going to call it negative 4,500,000. That's going to be equal to negative 500,000 Newton per coulomb. So we can say the magnitude is going to be 500,000 Newton per coulomb, but it's going to the left. Alright guys, that is everything. Thanks for following me with everything here. Next time we're going to be talking about magnetism. Thank you. Bye. Whoopsies.